morning. Myself Dr.A.Vaniprabha, Associate Professor, EC Department working in SNS College of Engineering. Today, my lecture series is on mobile radio propagation. The first portion of this series is free space propagation model. Free space propagation model. From the word, it implies the transmission is between free space medium, which is between the transmitter and the receiver. Propagation is a traveling of waves from one point to another. Here the transmitter and receiver are placed in open air or free space. There are two basic ways of transmitting a signal, either through a guided medium or through an unguided medium. Guided mediums are such as coaxial cables and fiber optic cables. These are preferred because they are less hostile toward the information carrying the electromagnetic signal than the wireless or the unguided medium, though it presents challenges and conditions which are unique for this kind of transmission. Free space propagation model, we assume a transmitter and receiver is placed at a distance d. The transmitter is able to transmit the signals in many directions and the receiver could be able to receive the signals from many directions. Even then, the receiver, which is in sight with the transmitter, gains the signal with maximum power or good signal strength. That is referred as line of sight. For a clear line of sight between the transmitter and receiver, the received signal power will be having the maximum signal strength. For example, the satellite or microwave communication can be the best example for clear line of sight. So assume received power decays as a function of distance between the transmitter and receiver. As the distance increases, obviously the signal strength also decays. This is represented by the Friis free space equation P hour of D, which is equal to the product of the transmitter, gain of the transmitter and receiver, and the square of the signal wavelength divided by 4 pi square product of the square of the distance into system loss factor L. Though care and concerned design, any system which has been designed for wireless communication exhibits some loss factor. L is much greater than or equal to 1 indicates the loss due to transmission line attenuation, filter losses and antenna losses. If L is equal to 1, this indicates there is no loss in the system hardware. The gain can also be referred in terms of the physical structure of the antenna. G is equal to 4 pi AE by lambda square, where AE is the effective aperture of the antenna. Lambda is the wavelength of the signal and it always depends on the frequency of the signal. Lambda is equal to C by F. C is the speed of light and the PT and PR are the transmitter and receiver power, and it is always represented in same units, either in watts or milliwatt. The gain of the transmitter and receiver are dimensionless. An isotropic radiator, iso means equally in all directions. So this radiator is an ideal radiator which radiates the signal power with unity gain uniformly in all the directions, that is in 360 degrees, and is often used as a reference radiator or reference antenna. Effective isotropic radiated power, named as EIRP, is defined as the product of the transmitter power and the gain of the transmitting antenna. This represents the maximum radiated power available from a transmitter in direction of the maximum antenna gain as it communicated towards the receiver. Practically, effective radiated power is used instead of effective isotropic radiated power. Effective radiated power is the radiated power which is compared to the half wave dipole antenna. Since the dipole antenna has the gain of 1.64 or 2.15 dB, ERP is equal to effective isotropic radiated power minus 2.15 dB. The ERP will be 2.15 dB smaller or lesser than the ERP for the same transmission medium. We'll discuss the remaining topics in the next lecture. Thank you.